Welcome back. In this video we're going to talk about the algebraic properties of the cross product that come directly from the component definition of the cross product that we constructed in our previous videos. We need to establish these by allowing ourselves general vectors and then studying what happens when we combine them together in different ways. So we'll have three vectors x, y, and z, and then we'll have a single scalar that we call alpha that's in the real numbers. We'll let the components of each x, y, and z be as follows, where x is x1, y1, z1, y is x2, y2, z2, and z is x3, y3, z3. We'll start our discussion of algebraic properties with the first one, which is called anticommutative. We briefly discussed this in our beginning conversation about what happens when you take I cross j versus j cross I, and we saw that on the right hand rule I cross j positive k, whereas if you took j cross I, so you're going to have to do this at home, negative k, and we see that those are negatives. I want to go ahead and establish that formally by actually doing this out. So here we have x cross y is going to be given by this. We saw that we can actually get the component form. Each component is given by canceling out that. So the first component, cancel out the x's, and then take the area of the parallelogram, which is y1 z2 minus y2 z1. So that was the first component. Second component, I cancel out y2. I take the area of the parallelogram, which would be x1 z2 minus x2 z1. But remember, we flip the order because the second component has a negative scale. So this would be x2 z1 minus x1 z2. I'm doing this formula from memory, not from looking at another sheet of paper. Because I've spent the time encoding it in my mind, I encourage viewers at home to do the same. Encode it in your mind so you don't have to look at pieces of paper to remember. All right, last one, we said we cancel out the z component, and then we take the positive area, which in this case would be x1 y2 minus x2 y1. All right, so now that is the cross of the two of them. And the claim is that if we factor out a negative here, let's go ahead and do that. So here I factor out a negative, and I'm going to switch the order when I do that. So this would be now y2 z1 minus y1 z2. Here I switch the order. This would be x1 z2 minus x2 z1. And then finally this would be x2 y1 minus x1 y2. Notice when I switch the order, this now would be the second component of the first vector by the definition, the component form. This would be the third component of the second vector. So here the z1 is over in this area. All right. y1 would be the second component of the second vector, just by the way that this works out, and z2 would be the first component of the, the third component of the first vector. Same thing, x1, because these orders are switched, would go here, and x2 would go there. If you don't see that immediately, it's probably because you haven't spent hundreds of hours cooped up in your room alone, not talking to anybody, thinking about this, and that's okay. That means you have a life. Keep going with that. Yeah, but the point is that indeed these things are anticommutative, and we've just established that formally using our definition. Let's move on to the next algebraic property of the dot product, which we're going to call homogeneity or homogeneous. Anytime you see homogeneous, generally it has to do with behaviors of scalars. So in this case we're looking at if you have any scalar, that little dot right here would be a scalar vector multiplication because alpha is a scalar, x is a vector, and then you take that scalar vector multiplication and you cross it with y. The claim is it doesn't matter where you do the scalar multiplication. You can do the scalar multiplication in the first coordinate, the first argument, you can do it in the second argument, or you can do it outside the entire thing. Be careful, this dot right here is also scalar vector multiplication because the cross product is a vector. All right, so here we go. Let's go ahead and look at alpha x crossed with y. So here we have alpha times x by the definition of x. Here is y. When we cross these two things together, we're going to go ahead and do this. To get the first component, we cancel out this one, and then we take the area that results. So this would be alpha times y1, and we have z2 there, and we subtract away from that y2 alpha z1. I wonder if I'm going to have enough space here. I don't think I am. So I'm going to go ahead and do this a little bit under. This kind of irks me, but okay, I'll forgive myself. Here we go. We take the second component by canceling those out, and then we find the area of the parallelogram in reverse. So in this case, we have x2 times alpha z1 minus alpha x1 times z2. And then finally, we cancel out the z components, and we just do the straight area of the parallelogram, alpha x1 y2 minus x2 alpha y1. Notice that we can factor out an alpha from every single scalar involved here. I'm going to do that all at once. This is actually, let's see, 1, 2, 3 different factors plus a scalar multiplication. Now I have y1 z1 minus y2 z1. Of course I meant y1 z2 because that's a z2. And then again here I factor out an alpha. I've got x2 z1 minus x1 z2. That was the opposite order. Oh my god, I'm running out of room. x1 y2 minus x2 y1. And notice this is indeed alpha times the cross product x cross y. And if you're really excited about math and life, you could confirm for yourself, and I encourage you to do this, that you get the same result if you have the alpha in the second component. So you could do that just by repeating this process and indeed showing that you can factor out the alpha. I'll leave that for the viewer's pleasure. Okay, so we've got homogeneity of the cross product. We have anticommutativity. Anticommutativity means you factor out a negative. Finally, we're going to look at distributivity of the cross product over vector addition. And there are going to be two forms of distributivity. They're going to be what we call right distributivity and left distributivity. So here we have right distributivity. Right distributivity, we're going to say, let's take x cross y plus z. So here we go. Cancel out the first components, and I'm left with y1 times the second component here, which was z2 plus z3. And this is a vector. And then we subtract away from that the second component, which is y2 plus y3 times z1. So that gives me my first component there. Next, for the second component, we can cancel out the middle terms, and then we take the area of the parallelogram in reverse order. So in this case, we start with x2 plus x3. That's the first component of the second vector. We multiply that by z1, and then we subtract away from that x1 times z2 plus z3. Of course, this is plus z3. So of course up here, this is a plus symbol, not a times symbol, because this is vector addition. And the last entry comes from canceling out this one, and then literally just doing the area of the parallelogram associated with the projection onto the xy plane, which would be y2 plus y3, minus, in this case, we would have the x coordinate there, which would be x2 plus x3 multiplied by y1. And we can close that. And what's really interesting about each of these is that this is a scalar multiplication over a vector addition, which means we can actually distribute each of those based on our knowledge of scalar multiplication. So here we got y1z2 plus y1z3, and then we subtract away from this. Let's do both distributions at once. y2z1, and we'll also subtract away y3z1, so that's in the first component. Here we would have x2z1 plus x3z1, and then we subtract away from that x1z2 and also x1z3. And then finally we have x1 y2 plus x1 y3, and then we also would have x2 y1 minus x3 y1. I hope you're noticing that this is where those habits of writing math really clearly come in. Hopefully by the end of this I will only have to repeat this proof once, and I'm doing this out of my mind, not by looking at pieces of paper. And why I want to tell you that is that the way that I write math affects how I can do it. The more clear my writing is the first time that I write it, the easier it is to follow along. Okay, so in this case, I see that this is going to be my first case, and I'm going to separate that other one out individually. So here I'm going to go ahead and add this to the second component. So this would be y1 z3 minus y3 z1. So now that takes care of that whole first line. Here, the second one that I see is going to be necessary is x2 z1 minus x1 z2. And then I'm left over with x3 z1 minus x1 z3. And that was by separating those. And then the last one looks like x1 y2 minus x2 y1. And then we have x1 y3 minus x3 y1. It's a little bit non-trivial to see that this actually works out to be, this first one is exactly x cross y, and the second one is exactly x cross z by the component definition. And by writing it really clearly the first time and going super slow, I could see this immediately. And we've just confirmed that the cross product is right distributive. Now I have a gift for you viewer at home. These are always fun. The gift is to finish the distributivity argument for the other case. So the other case of distributivity says that if you have vector addition in the left argument of the cross product, that I can distribute the cross product over that vector addition, and I would get this scenario. So x plus y quantity cross z is x cross z plus y cross z. I leave this to you, the viewer, to confirm for yourself, and you can use the last algebraic proof that we just did, or algebraic argument, to write your own algebraic argument. And I would say follow the structure there. As a mathematician, what I've learned is it's better to write clearly and to go slow to get it right the first time when you're doing the argument early on than it is to not pay attention to what you're doing and then have to repeat yourself. In the next video, we'll talk about some theorems that come out of the component definition of the cross product, and then we'll move on to some examples. I'll see you in the next video.